The universe is a huge place filled with amazing things. One of the most amazing things we can see are supernovae. Imagine a star way bigger than our sun, ending its life in a huge explosion. That's a supernova, a giant explosion that happens when a star dies and something new is born. These explosions throw out heavy things like gold and iron that were made inside the star. These things then help to make new planets and even life. Let's learn about supernovae and how they affect the universe we live in. A supernova is basically a star exploding at the end of its life. It's a huge explosion that sends out a massive amount of energy. To understand how much energy, imagine our sun shining for billions of years. A supernova can release more energy in a few weeks than that. But these explosions aren't just pretty lights in the sky. They're really important for the universe. Supernovae create and spread heavy elements, the building blocks of planets, life, and even us. Without them, the universe would be very different, without the amazing things we see today. By studying these explosions, we can learn more about how the universe works. Not all supernovae are the same. There are different ways a star can explode. Astronomers have found two main types: core collapse supernovae and thermal runaway supernovae. Core collapse supernovae happen when the inside of a giant star, much bigger than our sun, collapses. These stars live fast and die young. Eventually, their core can't hold itself up anymore and it collapses, causing a huge explosion. Thermal runaway supernovae, also called type Ia supernovae, happen differently. They happen in systems with two stars orbiting each other. One star, a white dwarf, steals matter from its neighbor until it gets too heavy and explodes. To understand supernovae, we need to understand stars. Stars are the fundamental building blocks of the universe, illuminating the cosmos and driving the chemical processes that make life possible. They are born, they live, and they die, each stage of their life cycle contributing to the grand tapestry of the universe. Stars, like our sun, aren't forever. They're born, they live, and then they die. The life of a star is a complex and fascinating journey, beginning in the dense regions of space and ending in a spectacular finale. Our sun, for instance, has been shining for about 4.6 billion years and will continue to do so for another 5 billion years. How a star dies depends on how big it is. Smaller stars, like red dwarfs, burn their fuel slowly and can last for tens of billions of years. Larger stars, however, burn their fuel much more quickly and have shorter lifespans. The mass of a star determines its ultimate fate. Stars are born in huge clouds of gas and dust. These stellar nurseries are scattered throughout galaxies, providing the raw materials for star formation. Within these clouds, regions of higher density begin to collapse under their own gravity. Gravity pulls these clouds together, and they get hotter and hotter. As the material collapses, the temperature and pressure at the core increase, eventually reaching the point where nuclear fusion can begin. Eventually, the center gets so hot that it starts nuclear fusion, the process that makes stars shine. This fusion process converts hydrogen into helium, releasing enormous amounts of energy in the form of light and heat. For most of their lives, stars are balanced between gravity pulling in and energy pushing out. This delicate balance keeps the star stable, allowing it to shine steadily for millions or even billions of years. But this doesn't last forever. As stars age, they exhaust their nuclear fuel, and the balance between gravity and pressure shifts. As stars get older, they use up their fuel. For stars like our sun, this means expanding into a red giant and shedding their outer layers. Stars like our sun will eventually expand and gently release their outer layers. This process creates beautiful planetary nebulae, leaving behind a dense core known as a white dwarf. Massive stars, however, have a much more dramatic ending, a supernova. These colossal explosions are among the most energetic events in the universe, outshining entire galaxies for a brief period, and scattering heavy elements into space, seeding future generations of stars and planets. Core collapse supernovae are the spectacular deaths of giant stars at least 8 times heavier than our Sun. These cosmic behemoths live their lives in a blaze of glory, burning through their nuclear fuel at an astonishing rate. Unlike smaller stars, which can burn for billions of years, these giants have much shorter lifespans, often only a few million years. These stars live fast and die young, using up their fuel very quickly. As they burn through their hydrogen, they begin to fuse heavier elements in their cores. This process continues until iron is produced, which cannot be used as fuel in the same way. As the core fills with iron, it becomes unstable. Iron doesn't produce energy when it fuses. Instead, it absorbs energy. This leads to a catastrophic imbalance within the star. The core collapses in on itself incredibly fast. In a fraction of a second, the core's collapse triggers a rebound effect, sending shock waves outward. This creates a shock wave, a powerful burst of energy that travels through the star. The shock wave is so intense that it rips the star apart, causing the outer layers to explode violently into space. This energy blows the star apart in a massive explosion, a supernova. The explosion is so bright that it can outshine an entire galaxy for a short period of time. If the core isn't too heavy, it becomes a neutron star, a super-dense ball of matter. Neutron stars are incredibly dense, with a single teaspoon of their material weighing as much as a mountain on Earth. If the core is very heavy, it becomes a black hole, a region of space-time so dense that nothing can escape its pull. Black holes are among the most mysterious and fascinating objects in the universe, warping space and time around them. Thermal runaway supernovae, also called type Ia supernovae, happen in systems with 2 stars orbiting each other. One star is a white dwarf, the leftover core of a star like our Sun. The other star could be any type of star. White dwarfs are incredibly dense, like squeezing all the stuff in our Sun into a ball the size of Earth. They can pull matter from their companion star, growing bigger. If the white dwarf gets too heavy, it becomes unstable and explodes in a runaway nuclear reaction. Unlike core collapse supernovae, which leave behind neutron stars or black holes, these supernovae completely destroy the white dwarf. Even though supernovae happen very far away, we can still see and study them. These colossal explosions mark the end of a star's life and release an immense amount of energy, lighting up the cosmos. They're so bright that we can sometimes even see them without telescopes. Imagine looking up at the night sky and witnessing a star suddenly outshine its neighbors. Astronomers use telescopes and other instruments to learn about these explosions. By observing the light and other emissions from supernovae, they can gather valuable data about the universe. One way they find supernovae is by looking for new bright spots in the night sky. These new points of light can appear suddenly and are often the first clue that a supernova has occurred. Special telescopes scan the sky and compare pictures taken at different times. By analyzing these images, astronomers can detect changes and identify potential supernovae. If they see something new and bright, it could be a supernova. This discovery process is crucial for understanding the life cycles of stars and the dynamics of our universe. Astronomers also use a technique called spectroscopy to study the light from supernovae. By breaking down the light into its component colors, they can learn about the elements present in the explosion. This tells them what the supernova is made of. Different elements emit light at specific wavelengths, allowing scientists to identify them and understand the composition of the star that exploded. Space telescopes, like the Hubble Space Telescope, have helped us understand supernovae even better by observing them in different kinds of light. These observations provide a more complete picture of these cosmic events, revealing details that ground-based telescopes might miss. With the help of advanced technology and international collaboration, our knowledge of supernovae continues to grow. Each discovery brings us closer to understanding the vast and dynamic universe we live in. Supernovae are important for the universe. They create the building blocks of planets and life, including the elements that make up our bodies. The incredible heat and pressure during a supernova create heavy elements like gold, silver, and uranium. These elements are then spread out into space, mixing with gas and dust to form new stars and planets. Supernovae also help to create new stars. The shock waves from these explosions can cause clouds of gas and dust to collapse, forming new stars. They even affect entire galaxies by heating up the gas between stars and influencing how galaxies grow and change. Supernovae are amazing events that mark the end of a star's life, but are crucial for the birth of new stars and the creation of elements. We've learned about two main types of supernovae: core collapse supernovae, where massive stars collapse and explode, and thermal runaway supernovae, where white dwarfs in binary systems explode. By studying supernovae, we learn about the lives and deaths of stars, the origins of the elements, and how the universe evolves. These explosions are like cosmic engines, driving the cycle of starbirth, death, and rebirth.